Yeah, so yeah, spotlight on me. I was so careful to draw everything last time, but it takes so long to be careful. So I'm just going to be deliberate. Now, the reason why I'm trying to be so deliberate is because I'm trying to think of what's happening. There's a box at the reference level, a table or something, and there's a box that is pulled 90 degrees with respect to that reference level on a light cable of length L. Okay, everybody following that okay? I know I'm very close to the top there. I want to make sure you can see it. When it swings down, that box will have its own kinetic energy. But the other box will be still. Then there is a collision, and both boxes stick together, essentially making a single box of combined mass with a single velocity. And then from there, the two boxes swing upwards, briefly coming to rest before they swing back down. Does this sound like the events of the problem? Now, I didn't draw it like this for my own benefit. You should, however, because what you have to start to come to understand is when is this problem a conservation of energy problem? When is it a circular motion problem? When is it a projectile problem? When is it a conservation of energy problem? What can you count on? When the problem discusses the mass swinging downward, it's talking about one mass changing height and gaining velocity. That's conservation of energy. And then there's a collision. A collision is only the instantaneous moment before contact and the instantaneous moment after contact. That's all collision. But during those instantaneous moments, the momentum has to be conserved. Look, the momentum was not conserved here. The object's velocity was continuously getting greater. It was not conserved there. And the momentum is not conserved here. The momentum of the system is leaving the system. But there is this part in the middle, the collision, where momentum is conserved. So momentum is conserved here. Now, after that, they've joined together. They have a combined velocity. Probably less energy, but I don't know for sure. But now this single object converts its velocity to a height. This sounds like conservation of energy. You want to get these problems right? Break them up into stages. I see 3 stages to this problem. Stage 1 is a conservation of energy problem. 2mgl equals 1/2 times 2m times v squared. Question about that? The mass was 2m. After this is a conservation of momentum problem. One box is moving. It has velocity v. So the momentum of the system is 2mv. After the collision, both boxes are moving at the same velocity. They joined together. So they have some final velocity related to that. But afterwards, this new system has kinetic energy different from the energy we had before. I'm sure a follow-up question asking about the ratio of the final energy to the original energy would be a great question. But this is going to be converted into gravitational potential energy. But I remember things about angles and stuff, so I'll probably have to write the height that it goes to in terms of an angle. That's a problem right there. It's a great problem. Working it out, I'll tell you what the answer is so that I don't have to do the answer key later. It's going to be cosine of theta equals 5/9. That's the answer. Work it through. If you want me to, I'll do your algebra. But do you see how I've broken the problem up? Now, we can talk about all of these questions that have this in them because they're all very similar. Let's look at this next one. This one has a loop in it. Eek, Mr. Sheldon. This might be the part where somebody else draws. I usually draw circles great, but only on the board. I'm a great board circle drawer. Got to use the tool. So I need all right, so there is a block. Isn't the block located right at the base of the circle? And then is there another block being fired at it? Is that the initial setup for this problem? Yeah. And then there's going to be the point where there is a collision and both blocks join together and have a combined velocity. And both blocks make it to the top here with a combined velocity. Do you guys see that okay? These represent the states of this problem. I see that from here to here, conservation, why am I writing conservation? I don't want to write that down. Conservation of momentum. None of this stuff that happened here matters. Pictures tend to draw this thing really far away just to mess with you. All that matters is that instantaneous moment before the collision and the instantaneous moment after the collision. That's conservation of momentum. But that has to give the system kinetic energy after the collision. What decides whether it can make it to the top or not is energy. Is there enough energy to make it to the top? But then there's a condition placed on that energy that it can only successfully be at the top if the net force equals mv squared over r. That's a condition, that's separate. Conditional parts of the problem might affect what I need to have happen, like the velocity here has to be suited correctly so that I get to this point with the right velocity. But the right velocity is situational. In this case, it has to have a situation that depends on the centripetal velocity, the centripetal acceleration. So again, this problem, they don't give us the beginning part like they did in the first problem. They give us the situation. They tell us the radius and the masses of the blocks. That's telling us that we probably have to figure out where to start this problem correctly in order to get the answer. If I remember right, they want this velocity. Is that right? How fast does the first block have to be going so it stays in circular motion? So I'm pretty much thinking that this problem has to be done this way, backwards. Don't you think? I think. Anybody want me to do this? Or is that enough to get you started? Be honest. Yep.
Can you just say what the answer is?
I don't know this one. I haven't worked it yet today. So I would have to do it. So I'm going to start here. Is it just R?
Yes.
So we've done this enough to know that it's mg equals mv squared over r. So the v has to be the square root of gr. That good? That's how fast I must be going when I'm here. So knowing that, I have kinetic and potential energy up there. The mass is 2m though, not that it matters, but up there it must be 1/2 times 2m times v squared plus 2m times g times 2r. Got to get the height right. This had to be equal to the kinetic energy I had at the bottom. What's that?
Nothing. We're talking about the mass.
You're talking about after the collision, it's 3m at the top.
Oh, is it 3m? They're not the same size mass? Okay. Sorry. I said I didn't do this problem. So which one is the heavier mass?
The one that's
The one it collides with.
So that's it, 1 and 2?
Yeah.
Okay. That wouldn't have affected this part, but I get you. Thank you. I appreciate it. So I see a way to get the velocity of the system after the collision. Now, there's a momentum problem that takes place just before this, where 3m v final has to equal m v naught. So it seems to me we want this. And it has to be in terms of all of that other stuff. So I need to find VF here, substitute it in here, and then solve for V naught. Looking across this problem, M will not be in my answer. Looking across this problem, G probably will be. So do you want me to keep going? I can do my physics. It's just algebra, but it does disappoint me. Cancel out all the 3M's. Multiply by 2, VF squared equals GR plus 2GR. So VF equals the square root of 3GR. Questions? All righty. 3m times the square root of 3GR equals mv naught. There's the answer. Oops. Yay. So, oh yeah. Not so bad, but please notice, I lay it out very clear. I am careful to know what all my transitions are. I like it. All right, so that's 1 and 2, isn't it? So 3 parts C and D. Which one's 3?
That's the 5 kilogram block and then the 3 kilogram block.
What's that? Okay. People get this one wrong, but a lot of times they get it wrong because they don't understand the conditions upon which the problem is based. So the way I did this problem in other classes was this. Before I placed anything on the spring, this is how long it was. But then I placed the 5 kilogram box on it. And when I did and allowed it to go to equilibrium, this is not dropping the box on it. Then it'd still be moving. I carefully set it down, absorbed the energy until it was equilibrium to find the equilibrium position. And that was 5 centimeters below the top of the original uncompressed spring. Then I placed another box on top of the first box. And the box descended another 3 centimeters. So now I am 8 centimeters beneath the location where the spring was at rest, where the spring was fully extended. Everybody follow that? That is all just mg equals kx. And the spring's 1,000 newtons per meter. Now here's the deal. The 5 kilogram box is attached to the spring, meaning the spring can both push and pull on the box. So if I took the box and pulled it out to here, say right there, there would be 2 downward forces on that box. There'd be kx, for however far I pulled it up, and there'd be mg. Everybody follow that okay? That means, of course, that the acceleration of this box is going to be greater than g because the net force is going to equal ma, and I have 2 forces pulling it down. You guys follow? Any question about that? Because that's important. Now that only occurs if I stretch the spring beyond this reference level. I have to get the box above that reference level for the spring to pull down on the box. This is important. If you don't understand this part, we can't move on. I don't want to hear about it later after I've left this part. All right, there we go. The 3 kilogram block will never experience a downward force from the spring. The 3 kilogram block can only feel a normal force from the block beneath it and weight from gravity, which means the 3 kilogram block will no longer be in contact if the 5 kilogram block feels an acceleration greater than g. So that's the limit. I can only experience an acceleration downwards that is g or less. If I experience a downward acceleration greater than g, then the boxes are going to separate. So if I want to stay in a condition, now it asks about pulling the box downwards and letting it go. It's the wrong way to do the problem. So instead, lift the box upwards to the point where we know the boxes won't separate. So I'm going to lift them right to here. If I lift them to here, the spring is in its relaxed state, right? It's not pulling down on the box, but if I let go, the initial acceleration will be g or less. So if I drop it, the system will accelerate downwards until it comes to rest when all the energy is in the form of elastic potential energy. Now, this will not give you the answer to the question, but it will tell you the point at which you could pull the box down and let it go, because it will go to the same height as we're starting at here. So how high is this? I don't know. This is mgh, and that's got to equal 1/2 kh squared, because the spring will be compressed the distance h. Factor out an h and set it equal to 0, because that's the condition that we're in right now. And then I can get the other one, which is 80 equals 1/2 of 1,000 times h. So h equals 16 centimeters. That is not the answer, though, because it asked how far could you push the box down from its relaxed condition. It wants to know how far from here would you push the box downwards. That answer is 8 centimeters, because we're already 8 centimeters below this place. And this shouldn't surprise you. Anybody who was in the class last year, notice it oscillates the same distance above as below. This is the equilibrium condition. So that's C and D, isn't it? Oh, I didn't do the speed of the block, but I think you can do that, right? The speed of the block is take it to here and then just see what the velocity is when it makes it to the 8 centimeter mark. So don't forget the kinetic energy there. This would be mg times 0.08 when it's here equals 1/2 mv squared plus 1/2 kx squared. The spring is compressed a little bit. So this will be the maximum speed as it passes through equilibrium. All right. Time for question 4? I like question 4 a lot, mostly because you guys have no idea how to do it. That's not why I like it. I like it because it allows me to have this quick conversation with you about motion of the center of mass. So let's have that conversation first, and then we'll talk about how the heck do you figure out when the spring is compressed and how much? Because I know that had to be on somebody's mind. I'm sure somebody, super smarty got it, but maybe not. I do want to point out something interesting, though. There are people who believe the spring won't compress at all. That's not even close. That's not true. How does the second box move if the spring doesn't compress? It has to compress some so that there can be a force on the second box. But let's do something fun for the beginning of this problem. And by fun, I mean fun for me. 2 boxes. Reference point. distance x1 to box 1, and distance x2 to box 2. Okay so far? The center of mass of the system would be m1x1 plus m2x2 all over m1 plus m2. Center of mass of the system. XCM equals that. We good? If I take the derivative of both sides with respect to time, I would get dxcm dt, which will be ddt of all of that. Right? We okay so far? Well, good, because this is the velocity of the center of mass. The result of this is m1v1 plus m2v2 over m1 plus m2. Velocity of the center of mass. There is an interesting thing here that only people who have taken this class before would notice. And that is the velocity of center of mass is the same as the velocity that you would get from a perfectly inelastic collision. If you know that, it's a shortcut. You could use it. I'll say it again. If you want a shortcut, not have to do this, the velocity of the center of mass is the same velocity you would get if your system had a perfectly inelastic collision, if all the masses stuck together during a collision. Now, that's no big deal. It is just something that, well, you should do. Now, knowing that, that answers the question, what is the velocity of the center of mass? And if you wanted to figure it out from the beginning, you could, because you have all the information to do so. If you want to figure it out after they have the spring compressed, you can do that too. I have to hurry because I'm going to run out of time here. I have 5 minutes to get to the end of this question. So let's set this problem up into pieces, right? In the beginning, this box is moving and the other box isn't. So there's going to be a moment where the first box finally contacts the spring. And at that moment, the first box has velocity, but the second box doesn't. At this instant. Everybody okay so far? During this instant, the spring is compressed a small amount. So that means there is a force on this box due to Kx, the amount that spring was compressed, but a force on this box equal to Kx because Newton's third law. The box on the right speeds up, the box on the left slows down. However, they're not traveling the same speed yet. This one is just beginning to move, but the other one is still moving faster. So you understand that the spring will compress a little more, the force will increase, and this box will speed up a little bit, and this box will slow down a little bit. Do you realize the spring will keep compressing until the box on the right and the box on the left have the same speed? Otherwise, they're still closing in on each other. But when they have the same speed now, that force is going to force them apart, speeding up the box on the right and slowing down the box on the left. So the instant that both boxes have the same speed, the spring is at its fully compressed condition. When both boxes have the same speed, when basically this is a perfectly inelastic collision. At that moment, all the momentum is in both boxes. So you'd have, is the first box the heavy one?
Yeah.
So this one's 2m, the other one's just m. So Our initial momentum is 2mv. Our final momentum is going to be 2m plus m times v final. Those two have to be equal. So v final equals 2/3 of v. This does not tell you how much the spring is compressed. Sorry. However, there's no friction in this problem, no air resistance, right? Although this is not an elastic collision, I can tell you where all the energy is. This is how much kinetic energy the system has before the collision. At the moment the spring is fully compressed, at that instant, the first box has that much kinetic energy. The second box has that much kinetic energy because they both have the same velocity. But the spring must also have some potential energy. So when you find out what that final velocity is, you can then use that in an energy equation to find out what that maximum compression is. I like this question. I like it a lot. Probably not tomorrow, but it's coming. Because this problem is actually done a lot of different ways. Like this one, for example. A block and a wedge. In this problem, if the system has no friction, then this is the same as the spring problem, except that this object stores gravitational potential energy during the collision. So there'll be a time when both of these objects have the same velocity, and when they do, it'll be 1/2 mass of the system times the velocity of the system squared plus mgh for the single mass. It'll have potential energy because then it'll slide back down. Same thing will happen. They've asked these two questions alternating off and on every 5 or 6 years. The maximum compression of the spring problem occurs a lot. This is question D and E on number 5. You want to practice this again? Do question D and E where they pull the pivot out of question 5. You have to figure out when that spring is compressed or what the maximum compression of the spring is. Folks, tomorrow I'm looking at a traditional question. So these, not so much, but you know, to me, no, not this one. Nothing wrong with one of these. I could see one with maybe a projectile, like this whole thing is at the edge of a table. And it has to, you know, hit the ground or something like that. All right. Enjoy. It's raining out there.
Mr. Shelton,
Yes.
for now.